Okay, I am just going to get started. Okay, so we've been talking about mappings, and last time we talked about mappings and submanifolds, and we had this um, characterization. Um, so with submanifolds, we had first of all, the inclusion is a CR mapping if all the other stuff is CR. And then you had this kind of what you would call a universal property of submanifolds, which is that a mapping into a submanifold is CR if and only if its composition with the inclusion is CR. And so what we're going to see is that exactly the same kind of statement holds for products. Okay, so let M1, M2, and N be CR manifolds. Um, uh, and let phi be a mapping from N into the product. Okay, so then two things. Just like the inclusion mapping was CR, the projection mappings are CR. Okay, and then the second statement is that phi is CR if and only if the projections composed with phi is CR. Of course, I only state this for two products, but by in trivial induction, it holds for finitely many products. You may wonder why we don't do this for infinite products. And it has to do with we had no problem with mappings which took values in large products, but we do have difficulty making sense out of mappings whose not making sense out of them, but being able to say anything useful about the product structure when the domain is a large product. So really, it has to do with the domain, not the codomain of products, being a product. Okay. So anyway, we work with finite products. Okay. So I'm not going to dwell on this. I'm just going to sort of say the key ideas, and then you can fill in the details. And I'll just say for part one, you have to, of course, the way you verify a mapping is CR is you write it down locally. So when you write down the local representative of the projection mapping, okay, then it's the projection mapping in the local spaces as well. So first, let me say the local representative, and so let me abbreviate that like this, of the product manifold is the product of the local representatives. So what I mean is that charts for the product are products of charts. Okay, and the local representatives of projections are the projections of the local representatives. Okay, so that's a slogan for the proof. That's not the proof. The proof basically just involves making applying turning these words into mathematical symbols, and I'll let you do that. All right, and of course it's worked out in the course text. All right, and similarly here. Um, what do you have to do? You want to show that phi is CR if and only if this is CR. Well, certainly if phi is CR, because we just sort of proved that the projections are CR. So if phi is CR and the projections are CR, then certainly this composition is CR. Okay. So it's the converse statement that's only requires proof. Okay, so we're going to suppose that oh, so sorry. I'm gonna, if you're writing at home, you hate this. I don't care. And so there's a picture that goes along with this that I should draw, and it's kind of the same picture as we had with submanifolds. The diagram is the following thing. So I have a mapping into a product. Okay. Then I have the projections. There's two of them, but I draw them kind of all together. Right, and then you have this mapping. So I'm really not doing anything by drawing this diagram, but this diagram is a representative kind of a thing, and it's sometimes a good way to organize your thoughts about things is to draw these diagrams, especially since there's certain kinds of diagrams that you find yourself drawing over and over again, and this kind of thing is one of them. And the reason is just this comes from this idea that I talked about last time um, um, about induced topologies for subsets of topological spaces being defined by this diagram. Okay. And similarly, the product topology is defined by a diagram like this. Okay, so these diagrams are helpful things very often. Okay. Right. Okay, so we want to show that if this is true, then phi is of class CR, but this is easy. But so let me quickly go through how you do this. So you prove it, of course, locally. So you take a chart. Let's say U psi V psi be a chart about y in n. Okay, and let u phi1 phi1 v phi1 and then right u phi2 I'm sorry phi2 v phi2 be charts about, let's say, um, x1 in M1 and x2 in M2, where x1, x2 is phi of y. Okay, so I have charts for each of M1 and M2, and so I work with the product chart. Okay, so what I know is I know that the local representatives, so I know that I have a mapping from N into the product, okay? And so that really means that I have two mappings. I have a mapping from N into M1, and I have a mapping from N into M2, and those mappings are, oops, are exactly these, all right? And I know that these are CR, okay? Um, and so really you're just lying those alongside each other and saying that the product of the things is CR, okay? So we are assuming the local representatives um, of P, R, A, phi, okay, um, as mappings. Okay, so what are these local representatives? So these are mappings from uh, psi of u psi to um, phi a of u phi a are CR. But then the local representative of phi is the product of these two local representatives. And product of and it's not the product. So um, okay, so let me maybe write down what that mapping is. Um, and so I was kind of hoping to avoid having to use symbols here, but maybe I have to. So I have the local representative. Okay, so it's the local representative of phi with respect to the chart psi and phi1 cross phi2. Okay. Okay, so this is going to be of a point in here. Okay, so let me write that point as, let me write it as y. Okay, and that's going to be simply phi psi. So then, oh, sorry, it's going to be not that, it's going to be PR1 composed with phi. Okay, so the local representative of this map with respect to the charts like this of y. Okay, and then PR2 phi in the local representative in these charts, okay, of y. Okay. All right. And so we have already seen when we talked about calculus. So, when you're proving that a certain mapping is of class CR, probably we're going to have to go back to calculus. And so we are. And so we have this mapping which maps y into a product like this. And we saw that a mapping into a product is CR if and only if each of its components is CR. And so the components are these, and we're assuming those are CR. Okay, so there. Okay, so that's products. All right. Okay, good. Okay, so now we're going to move to a completely new. Oh, sorry, before I do that, yes, that's why I put this reminder here, so I wouldn't um, jump ahead past this topic because I often miss these little topics because I'm in a rush to move to the big one. Okay, vector valued mappings. So there's some structure here that I want to talk about for very specific kinds of mappings. Okay, so we're going to let M be a CR manifold. And we're going to let V be a locally convex space. Okay. So locally convex spaces are open subsets of locally convex spaces. So they are manifolds. Okay. So I can talk about the space um, CRF of mappings of class CR from M into V. Okay. And all I want to do is point out that in this particular case, this because of the structure of V being a vector space, okay, this space has a bunch of algebraic structure, okay, and I want to point that out because, well, first of all, the space does have this structure, and the structure generally does not exist for general manifolds. It depends on the codomain here having its own algebraic structure, okay. So this space of mappings has various algebraic structures. Okay, so first of all, it's a vector space. Okay. Um, and what's the vector space structure? So it's and so so you'll remember back in assignment number one, I asked you to talk about uh, pointwise addition and multiplication of functions on a set, right? Um, and so that's we're using pointwise operations here, which is very common when you talk about function spaces. Okay, so if you have two mappings, let's say phi and psi. Okay, so these are mappings in here, all right, from M into V, and you want to add them. As soon as you write this down, you realize that the only thing you can do that makes any sense with the symbols at hand is that. So you should make sure that that makes sense, first of all, and of course it does, because once you evaluate these things at a point, they become vectors in V, so it makes sense to add them. All right. So that's vector addition, and then scalar multiplication. Again, once you write this down, there's only one possible thing to do. It's that. Okay. So, I guess in principle, you should go and verify the vector space axioms here. And they always amount to the vector space axioms holding in the codomain V. Right? Verifying vector space axioms is always tedious because there's so many of them. All right. So that's good. So now let's look at the case of V equals F. Okay, so now these are not vector space valued functions, but scalar valued functions. Okay, so denote. So these are just sometimes these are just called functions like that. Okay, so we just um, eliminate the codomain because it's understood to be the scalar field. Okay, and now let's look at this space and see what its algebraic structure is. Okay, all right, so CR FM is a ring. Okay, so we know already from part one that it's still, oh, sorry, was there a question? I heard a noise. No? Okay. An accident. Um, okay, so we know that this space certainly has these vector space operations, and what I'm saying is that it has not just these vector space operations, but it has the operations of multiplication, right? So there's two operations on here. One is addition, one is multiplication. The addition is the same as here, and multiplication, of course, is pointwise multiplication. Um, so addition, let me just say, is as in one. Okay. And um, the multiplication. So if I take two functions, f and g, and I want to multiply them, and again, there's only one way to do this. So you're using here the fact that the codomain has this algebraic structure of a product, and you use that to define the product of functions with values in that set with that algebraic structure. Okay. All right, so you have to do some verifications here, right? But you can do that. Okay. So in fact, this shows that CRFM. It has three algebraic structures now. It has addition, scalar multiplication, and then ring multiplication. Okay. And they're compatible in obvious ways, right? So if you put, a scalar in there, then the scalar comes out front, right? So all of that structure that shows that is an F algebra. That's the name of the structure. So i.e., it is an F vector space with a ring structure. This is what an algebra is. So it's a vector space with a ring structure that is compatible. And I'm not going to define what compatible is here. We'll maybe talk about algebras more when they arise later on in a certain context. Okay, but here I'll just say compatible. And like I said, it's obvious what compatible means. It means that scalar multiplication interacts with ring multiplication in a natural way, and it means that ring addition is the same as vector addition. Okay, that is compatible with the vector space structure. Okay, so, but for now, we're just going to be interested in the ring structure. Okay. Okay, so we saw here, so maybe let me be, because let's see, here, we're going to say that this is a module. Okay, so I guess we have all seen rings and vector spaces. Maybe we haven't seen modules. So modules are two rings as vector spaces are two fields. So in other words, just like a vector space is defined over a field of scalars, and you have scalar multiplication, a module is defined over a ring, and you have scalar multiplication, but the scalar multiplication is now of elements of your ring. So in this case, the elements of the ring are functions. And so what all this is saying is that there's a natural operation where you multiply a function a mapping with the values in V with a function, a scalar valued function. So, okay, so I need two operations here. I need I need vector addition, and that's the same as above. Okay, so and I also need multiplication by um, functions. Okay, um, okay, and so here f is in space of functions, and phi is in the space of vector valued mappings. Okay, and again, once you sort of write that down, that's obvious what the definition is. Okay, and so you use the fact that when you evaluate phi of x, you get something in V, and when you evaluate f of x, you get something in F. Okay, and so this product here is just the vector space operation in V. Okay, so you can multiply um, vector valued mappings by functions. Okay, all right, so that's all I wanted to say there. So actually, sorry, I'll say one more thing. Okay, so in this case, let's see, I think I don't want to do, yeah, sorry, I don't want to do that now because we don't have the structure to do it. So I'll stop there. Okay, so there's some algebraic structure that you get when the functions, the mappings take the values in vector spaces. Okay, good. All right, now, next topic. All right, so I'm going to be engaging now in, kind of a lengthy discussion, which if you haven't seen this stuff before, is going to seem um, like it's hard to understand why I'm doing this. So let me maybe start by um, motivating why I'm doing this. Okay, so we have spent some time in the last couple of lectures talking about mappings of and how a mapping can be of class CR. But we haven't yet said what the derivative of these mappings are. Okay, so what we're doing here is we're developing the structure for talking about derivatives of mappings. Okay. Um, and so to sort of give you some idea of what that structure is, what I'm going to do is just remind you of the things we've done locally. Okay. Um, but I'm going to do it in a package, what we've already talked about in a slightly different way, which is going to be more compatible with the direction that we're heading in. Okay, so let's do this. So let U, O, U, and V, O, V be locally convex spaces. Then let N and O be open. Okay. All right. So if phi is, let's say, a C1 mapping from N into O. Okay. So here I can think of N and O as in two ways. I can think of them as being open subsets of locally convex space, and I can also think of them as being manifolds. So either way, okay. But I'm definitely going to be using the structure of these things sitting inside a locally convex space. Okay, so phi um, is a mapping like this. So then okay, so then I have the derivative d phi. So this is a mapping from sorry n cross u into v. Okay, all right. So this is so it's x and u maps to the derivative. So these are the directional derivatives, of course, that we talked about, like that. Okay. Okay, so I'm going to write these as write this as um, um, T phi. Okay, so this is going to be a mapping from n cross u into O cross v, and it's going to be the mapping which takes a point x, u, 2. And all I'm going to do now is I'm going to not just keep track of this directional derivative, but I'm also going to keep track of phi of x. Like that. Okay. All right, and so this, has the benefit of making the domain and the codomain kind of look like they're symmetric, right? They kind of have the same features. It's your subset um, times the vector space in which it sits. So, and as we'll see, this has a nice geometric meaning. Okay. Um, so I can also write, so if, let's say phi is not just C1, but maybe C2. Okay. We can talk about its second derivative. Okay, so d2 phi. Okay. Um, and this is going to be a mapping from. Okay, so what's this going to do? So this is going to be a mapping from n cross two copies of u into v. Okay, and so it sends x u1, and we know things about this mapping. Sorry. Okay, so we know it's symmetric bilinear in U1 and U2. Okay. Okay, so what I'm going to do now is I'm just like I reorganized the first derivative, I'm going to reorganize the second derivative. Okay. And I'm going to call the resulting thing T2 phi. Okay, so what's this going to do? So this is going to map um, um, n cross uh, um, u cross u into O cross V cross V. Okay, so I'm going to kind of keep it symmetric. Um, and so what this is going to do is it's going to take an X and a U1 and a U2, and it's going to map it to, sorry, I'm going to need more space here. Phi of X, D phi of X, X, U1, and then D2 phi of x u1 u2, like that. All right. Okay, so what? All right. Okay, so what we want to do is we want to do that for manifolds. Okay, and so as I have said a couple of times, and now I'm going to say it for the first time in a really important way. We want constructions that we make to be independent of the sets of coordinates that we use. Okay, so in other words, if we had a chart, okay, and these sets N and O were the images of the chart domain, right? So these are now open subsets of the locally convex space, which serves as the model space. Okay, so in other words, so in other words, if I think of N as being like phi of U phi, okay, and O as being like, let's say, psi of U psi, okay, then you could imagine phi here is going to be the local representative as a mapping from here into here, okay? And so I have this local representative, and now I'm doing something with this local representative. Okay, and so what you want is you want for that local representative, the question you want to ask is this thing the local representative of some meaningful thing? Okay, and is this thing the local representative of some meaningful thing? And in order to define what meaningful means, that's where chart independence comes from. Okay, so I'm going to do a bunch of calculations here, um, just to kind of show you how independence of chart comes up. Okay, so now suppose that we have um, uh, n prime in U prime open and uh, O prime in V prime open. Okay, so I have some other locally convex space U prime and some other locally convex space V prime and open subsets N prime and O prime. Okay, so you can think of if my N and my O come from some choice of chart, this comes from some different chart. Oops. Um, these come from some different chart. And so then when I know if I have two charts and they overlap, I have an overlap map. And what's the overlap map? The overlap map is a diffeomorphism. Okay. Okay. So and CR, let's say, diffeomorphisms. Okay, so let me give a name to these. I'm just going to call them phi from N to N prime and psi from O to O prime. Okay. Then we have the mapping. This phi prime from uh, N prime to O prime. Okay, and so it's going to map a point X in N prime to, okay, so it's going to take a point in N prime, and it's going to map it to N, and then phi is going to map it to O, and then psi is going to map it to O prime. Okay, so it's going to be uh, um, psi composed with phi composed with uh, phi, little phi inverse. Okay. All right. So, all right. And let me, um, Okay, so let me simplify my life here. Um, because I don't want to get into all the nitty-gritty. All I really want to do is I want to see how the chain rule shows up here. Okay, so suppose for simplicity, because it'll illustrate what I'm after, that um, phi uh, that n prime is equal to n, and phi prime is the identity. Okay. All right. So what I want to do, just so in other words, I'm just applying a sort of change of coordinates, okay, on the codomain. All right. Just to make this a little bit more concrete. Okay. So what I want to do is I want to sort of do these constructions here um, that I did above for phi. I want to do them for phi prime. Okay. All right. So then. Okay, so T phi. Well, actually, let me write the D's first. Okay, so D phi prime is D. Okay, so phi prime now is just psi composed with phi. All right. And sorry, let me put arguments in here. Apologies. Okay, so this is going to be X um, U. Okay, and so the way that the chain rule works, and we saw this is, so this is D psi of phi of x, d phi of x u. Okay, that's how the chain rule works in this, our world of calculus. All right, and similarly, d2 phi prime of x u1 u2. Okay, so we had a formula for this. We had a formula for the general derivative, and this was the so-called Fa-de-Bruno formula. And we can just sort of write it down explicitly by looking at this thing in this case. So, okay, so remember we're differentiating here with respect to x. Okay, so x appears here and here. Okay, so I have to differentiate with some care, but you can maybe believe after the dust has settled the following thing. So first I'm going to go d2 psi, okay, um, evaluated at phi of x, okay. Um, then it's going to be evaluated at right, okay. So then it's going to be evaluated at this thing, evaluated at u1. So d phi of x u1. And I don't want to scrunch this, so let me give myself some more space. Okay, and then here, so now I'm differentiating with respect to this x, and so I'm differentiating with respect to this x. I'm going to use the chain rule in exactly the same way as I did up there. So I'm going to here get d phi of x u2. All right, so that's the first, the derivative with respect to that term. Now I'm going to sort of hold this one fixed and differentiate with respect to that one. Okay, plus d psi of phi of x, then I get d2 phi of x u1 u2. Okay? Right. So you can see here that by introducing, essentially you can think of this mapping as being a new chart for my codomain. Okay. The second derivatives, the first derivatives look good. Okay. Second derivatives are a little bit messy. Right. So now I can write down the t's. Okay. I can write down um, t phi prime and t2 phi prime. And then once I write those down, I can sort of talk about what their structure is and how that's going to affect um, the things we talk about for the next couple of lectures. Okay. Okay, so t phi prime of x u, just xu, is going to be, so it's d psi of phi of x, d phi of x u. Okay. Oh, apologies. I forgot the first part. Okay, so it's phi prime, and maybe let me write phi prime as its composition. So psi composed with phi of x, and then this thing, like that. Okay? Because remember that t uh, keeps track of the mapping in the first component. Okay, now T2 is altogether more complicated, but it has some features, and it's the features that I care about because that's what I'm going to be essentially talking about for the next couple lectures. All right, so we get the same thing here. All right, so remember, essentially what you do here is you write down for T2, okay, you have the function, the first derivative, then the second derivative. Okay, so the function, then I'm going to stick in the first derivative, then I'm going to stick in the second derivative. Okay, so and so it's going to be d psi of phi of x, d phi of x u1. Okay, so that's the first derivative, and then the second derivative is all that mess from the previous line. Okay, and then I think I need another one. All right, so let's take a look at this and see if we can get anything interesting out of this. Okay. All right, so this mapping here, so we should keep in mind what the arguments here are. The arguments are x and u here, and x, u1, u2 here. And my interest here is in what kind of a function is this of x, u1, and u2. Okay. Well, here, this is a linear function of u. Okay, big long. Well, in the second component, it's a linear function of u. In the first component, I just have my original mapping. All right, so, but this thing is linear. Okay. All right. So, what about this thing here? Okay. Well, this is uh, remember that d2 psi is bilinear. Okay, so this one is sort of it's linear in u1, u2. Okay, this one, however, is not linear. This one is actually bilinear. Okay, so I get a term here which is kind of linear. Okay, and then I get this term, which is quadratic, essentially bilinear. Okay, um, And so you get a term which is linear um, in the first derivative, but not linear in the second derivative. But it's linear plus quadratic. Okay. Um, and so we get this, you get a sort of structured kind of a nonlinear function. So it's what's called an affine function, right? So it's linear plus, oh, and apologies. As I was saying this, I knew I was doing something wrong, and um, I know what it is now. And let me see if I can. Yeah, my mistake was here. Um, Let me see. Um, so here, I think I have an error here somewhere. Um, yeah, I think yeah, I believe my oops, yeah, my error is here. Yeah, okay. Um, I think this is right. So let me see. So when you're differentiating this thing, okay, you're differentiating. uh, just see if I can remember why this is the way that is. Well, certainly one reason is, here, let me, yeah, that's not a super satisfactory explanation. Let me see if I can remember why that should be a U1 there. Um, right, right. So, okay, so I'm taking this thing and I'm differentiating it. Yeah. mm, mm, I think here, sorry, let me just check this to make sure I actually have that right. So apologies, just give me a moment here. I want to make sure I get this right. This is one of those dyslexia moments where I get these things confused. Okay. Um, oh, okay. Sorry. I have this backwards. Apologies. So it's U um, two, oops, sorry, two here. Okay. And U1 here. Okay. So that still doesn't make it obvious why that's the way it is. Um, hmm. Yeah, I can give you a messy explanation in terms of partial derivatives. Um, uh, Here, let me just think. Okay, so we're differentiating this thing, and you're differentiating that in the x2 direction. Hmm. Yeah, yeah. Like I said, I can think of a messy explanation, but I can't think of a good explanation in this terminology. But anyway, apology. This is right, but I can't think of a good explanation for why it looks the way it is. Now let me go back to my original statements and notice that. What do I have? This one, again, is linear in U1, U2. Okay, the joint vector U1, U2. Okay, and this term is not linear, right? It's bilinear, so it's kind of, again, quadratic in U1. Let me just maybe say this. If you wanted to verify this formula, why this formula is correct, and I'm not going to do this, and that's how I wrote this formula down when I sort of derived it in the course notes, and then I just kind of wrote it down. But you could think of a mapping phi from Rn to Rm. So phi looks like x maps to phi1 of x1 xn phi n m of x1 xm. Okay, and then you can just start calculating partial derivatives. All right. And when you do that, you'll see how that formula, right? So just take, right, and sorry, and then you take another mapping, sorry, which is psi from Rm to Rm, and then you differentiate the composition. Okay, just directly calculate it using elementary, chain rule, product rule computations. Right, so it's an exercise that's worth doing because then you really get to understand where these things come from, and certainly this is how I understand them, and you'll see why you end up with those terms the way they are. Okay, so sorry, I can't. I wish I could offer a better explanation than that, but I can't. Um, but the point is that this mapping is not linear. That's the sort of upshot of this whole big long conversation, is this one is linear in U. This one is a term which is linear in U1, U2, but then plus a nonlinear term. Okay. And so what we want to do is we want to study some way of organizing this into a geometric structure, which will allow us to talk about derivatives of mappings between manifolds. Okay, so that's the origin of the next few lectures, where we're going to talk first about vector bundles, and then we're going to talk about what are called affine bundles. Okay. All right, so that's kind of the motivation. That's where we're heading for, is finding a geometric setting which explains this, kind of elementary chain rule calculations that you do, that you can do using just first year calculus. Okay, all right. Sorry, there's a thing here in the chat. Okay. Yeah. I don't know. Okay. All right, so let's carry on doing what we're going to do, which is to talk about vector bundles now. Okay, so vector bundles. Okay, so the first thing we're going to talk about is what's called local vector bundles. All right, so vector bundles are going to be, well, basically, they're going to be things which locally look like these things that we talked about up here. Okay, so they're going to be products of open subsets of a locally convex space with a locally convex space. So here we had the locally convex space being, the same. This is an open subset of U, but there's no reason this can be an open subset of one locally convex space, and this can be another locally convex space, right? So, and that's the setting that we're going to use. Okay. All right. So vector bundles are manifolds, and they're manifolds modeled on not just open subsets of locally convex spaces, but a product, again, a product of a locally convex space and an open subset of a locally convex space with a locally convex space. So the point is, we need something to say locally what a vector bundle looks like. And it looks like this thing, which we're going to call a local vector bundle. Okay, so a local vector bundle. What's on my screen? So a local vector bundle is a set, which I'm going to write as O cross, say, U1. So there's going to be a U0 and a U1, where so I have two locally convex spaces, U0 and let's say O0 and U1, O1 are all CS's, and O is a subset of U0. Okay, so that a local vector bundle is a very simple thing. And so again, it's just this thing that we talked about above. Okay, so if you want to, think about the domain of the derivative, like here, then that's not a bad thing to have in mind. Okay, so that's what a local vector bundle is. And so a vector bundle is going to be a manifold which locally looks like a local vector bundle. Okay, and not only that, but the overlap maps have to satisfy some particular properties that preserve the structure of local vector bundles. So what's the structure of a local vector bundle? Very simple, it's just a product. Okay. So we need to talk about um, mappings between local vector bundles, because that's what the overlap map is going to be. So definition. So and so when I write a local vector bundle, I'm going to write it as three pieces of data, just because it's easier to organize it this way. So I'm going to write a local vector bundle as U0, O, U1. Okay. All right. So that organizes all of the data for the local vector bundle. Okay. So suppose I have two local vector bundles. And there's some pictures to go along with this, which I'll draw in a second, but let's do all the symbols first. And let me write my two things in alphabetical order. So O, N, sorry, U0, U1. Okay, so these are two local vector bundles. So a CRF local vector bundle mapping as always, R is what, non-negative integer or infinity is a mapping. And so it's going to be a mapping phi from one local vector bundle, which is n cross u1, into the other local vector bundle, which is O cross v1. Okay. With, okay, phi of x u. Okay. All right. So phi takes a point xu in here and maps to a point in O cross v1. So it'll have two components. The first component is going to be phi 0 of x. The second component is going to be phi 1 of xu. Okay, where Okay, so 1. Phi 0 maps n into O, and phi 1. So phi 1, so again, a good model to have in mind for what this local vector bundle mapping is this thing here. Okay, right. So in the first component, it's a mapping, and in the second component, it's a mapping, which is linear in the second component. Okay. All right, so phi 1 is linear in the second argument. Here, second argument. Okay. All right. So again, so keep that example in mind. All right. Okay, so we'll say that a local, so a CRF local vector bundle mapping. Okay, so when we talked about manifolds, the overlap maps had to be diffeomorphisms. Okay, so they had to be mappings which were CR. They had to be bijections, and the inverse had to be CR. Okay, so the diffeomorphism is sort of an equivalence between open sets in the category of CR things. Okay, so now we want to have a vector bundle isomorphism. That should be an equivalence of things in the sort of world of local vector bundles, right? So it should be a bijection whose inverse is also a local vector bundle. Okay, so that's the idea. So let me write that all down. So a local vector bundle mapping phi from n cross u1 to O cross v1 is a CR local vector bundle isomorphism if, okay, so the mappings phi 0 and phi 1 should have some particular properties. Okay, so with the phi 0 mapping should be a diffeomorphism from N to O. Okay, and then phi inverse, okay, is should be a local vector bundle mapping. Okay, so so I should maybe say it this way. Actually, let me think about the best way to organize. Oh, maybe it doesn't matter. So phi is a bijection, and phi inverse is a CR local vector bundle mapping. Okay. Just like it did in diffeomorphism, the mapping and its inverse have to be class CR. Okay, and then you need for the inverse property to hold also on the linear bits. Okay, so the inverse of the linear mapping. Okay, so this right, so this mapping phi1 is linear in its second argument. Okay, and so I want to consider the inverse of that linear mapping. Okay, so the mapping is U1 maps to phi1 of x U1, okay, is phi inverse 1 of, okay, phi of x, um, uh, sorry, um, is v maps to that. Okay. All right, so let me draw a picture associated with vector bundle mappings, and it'll be hopefully a little more clear um, what they are. Okay. First of all, let's draw a local vector bundle. All right, so a local vector bundle is a product. So it's a product of an open subset of a topological vector space. So let me not make it so stupid looking. All right, whatever. Okay, so this is going to be my, let's say, my n. Okay. Um, and you maybe want to think of n for the purposes of visualization as being a subset of some, maybe like a two-dimensional plane, like that. Okay. And sticking out of it, kind of orthogonal to the plane. Orthogonal doesn't really mean anything specific here, but for the purposes of visualization, orthogonal are copies of U, or U1. Okay, so okay, so attached to each point in N, I have copies of U, U1, like this. Okay, so that's my um, domain, local vector bundle. Then I have a local vector bundle mapping phi, which maps to another local vector bundle, O. And again, you should think of this thing as being sitting inside, some locally convex space, and sticking out of, attached to each point in O, I have a copy of V1. Like this. Okay. Okay, so those are my two local vector bundles. And so what does a local vector bundle mapping phi do? Okay, well, I have a point here. Let me maybe call it X. Okay, so I know that points in N get mapped to points in O by phi naught. Okay, so in the first component, it's just a mapping from N to O. Okay, so my point phi naught of X is going to be like that. Okay, so it doesn't take this point X and map it up to a point up here or something like that. Okay, it maps a point on N to a point in O in the products. Okay, good. Then what does it do? Then the definition is so now I've taken care of X, right? So it takes X to phi naught of X, right? So then if I keep X fixed and vary U, okay, I know that that resulting mapping will be linear. All right. So it's going to map um, points in the copy of U1 attached to X. It's going to map it to points in V1 attached to phi naught of X. Okay. So let me maybe try to emphasize that by changing colors. Okay. So this blue copy of U1 here is going to be mapped to this blue copy of V1 here. Okay. And the mapping, phi1. Okay, so this is going to be, so maybe let me make that one blue too. Okay, so this mapping from one blue vector space to the other blue vector space, which is U1, maps to phi1 of X U1. Okay, all right, so it maps this guy to this guy when I fix X. Okay, and then it does that for each X, right? So this one here maybe gets mapped to this one here and so on. Okay, so that's what a vector bundle mapping does. And a vector bundle isomorphism, okay, means that there's another mapping, phi inverse, which goes the other way, obviously. And when I take points in O, okay, phi inverse maps that back to the original point in N, okay, by a mapping which is a diffeomorphism, right? So it's invertible. So phi naught is invertible with a CR inverse, okay? And if I take the mapping phi1 here, and I think of it as a mapping from here to here, okay, then the inverse mapping, phi inverse, is a linear mapping from here to here, which is the inverse of the mapping from here to here, the linear inverse. Okay. So that's the local structure of vector bundles. Okay, so you have these um, product structures of, and like I said, the way to think about it is to think of n as being like, and we'll see that this is called the base. Okay, and then attached to points in n are these vector spaces, and these are what are called fibers. Okay, all right. Okay, so that's how you should, that's local vector bundles. Okay, so now I can define what a vector bundle is. So a vector bundle is a manifold with a chart, okay, sorry, with an atlas, all of whose charts are mappings into local vector bundles, and the overlap maps are vector bundle isomorphisms. Okay, so let me just write all that down, and then we'll talk about it starting next class. Okay, so A, C, R, F, vector bundle. And again, as always, um, is a set. S, like a manifold, is a set. Okay, and it has some structure, and the structure is that it has an atlas. Okay, let me be CR plus, right? Okay. A, all right. And A, the charts from A have very particular properties with respect to local vector bundles and local vector bundle isomorphisms. All right, so one. Okay. Um, charts from A look like. Okay, so it's going to be a chart domain, and I'm going to write that as that's a V. Okay, so it's going to be V psi, and then V0. I guess I did it this way. B psi 0 cross V psi 1. Sorry, I ran out of space. Apologies. Eh, interesting. Okay, and then V psi 1. Okay. All right, so they look, remember, so this is now just a chart. Okay, so this is my subset, my chart domain. This is my chart map. This is the locally convex space, which is the co-domain of my chart map. Okay, so this is the thing which we had always called U phi, V phi before, but now it has a particular form. Okay, so and the particular form is simply the chart codomain is a product like this. Okay. And all right, um, the image of psi. Okay, so this is going to be a subset of V psi 0 cross V psi 1 is a local vector bundle. And it's going to be um, O psi cross V psi 1, where, of course, O psi is a subset of V psi 0 is open. Okay, so that tells us that the charts map into local vector bundles, right? So this means that my manifold, which is my vector bundle, locally looks like a local vector bundle. Then, of course, the overlap maps have to have some specific properties, and of course, the property is going to be that it's that they're local vector bundle isomorphisms. Okay, so the overlap maps. C are local vector bundle isomorphisms. Okay. Right. So let me maybe just finish the definition with the usual stuff um, that we say about when we built manifolds. Okay. Um, so such an atlas is a CR vector bundle atlas. Okay. Um, two vector bundle atlases, A1 and A2, are equivalent. And it's the usual definition we had for manifolds too. So two atlases, when we had manifolds, are equivalent if they're union is a vector bundle atlas, was an atlas. So here it should be the union is a vector bundle atlas. Okay. And then what did we have for manifolds? The next step we had for manifolds is that a differentiable structure, a manifold structure, is an equivalence class of atlases. Okay, so a vector bundle structure is an equivalence class of um, vector bundle atlases. Okay, so A, C, R, vector bundle structure. Of vector bundle atlases. Well, C, R. Okay. Um, okay, so next time what we'll do is we'll turn this pile of garble into something a little bit comprehensible. But the picture you should have in your mind is really just the picture that's represented here, where I have my, let's say that these sets here are overlapping vector bundle charts, okay? And the condition then is that the overlap maps are mappings that are local vector bundle isomorphisms, right? So it maps this set diffeomorphically onto this set, and it maps the um, the vector spaces attached to each point isomorphically onto vector spaces attached to each point. Okay. Um, all right. So next time we'll talk about the kind of structure that vector bundles have. Okay? All right. I'm done. So unless there's questions, I'll see you next week.